So we talked about flow last time. Who can remind me what a flow is? No one? Jonathan, what is a flow? Right, so it's an invertible transformation between data and noise, but it's a really funny kind of model. Like, there were a friend that asked me after the class, like, can you get CDF out of a flow? I'm like, not really. Like, there are very little ways that you can access a flow. Like, you can sort of sample a noise and then feed it through it and get the sample data. And then for any sample data point, you can feed it through back to noise variable and then evaluate its likelihood. But there's not too much other things you can do with it. So that's a kind of a funny thing about this model. And where we left off last time was a family of models called NICE and RealNVP. And what it is a specific way to construct this invertible transformation so that you can evaluate its likelihood efficiently as well as sample from it efficiently. And the rough way that it works is, this is just recapping what we have gone through last time. And essentially, you divide your dimensions into two halves. One half that you call from, let's say you have a random variable that has dimension d, then you divide the first half to be, the first dimension goes to d divided by 2, and then you have the second half. And then you treat these two subsets of random variables differently. And for the first one, you will just feed it through. So this is the noise that you sample, and then you will just say, my data is just exactly the same as the noise. So it's just identity function. And then the other half is somewhat more interesting. The other half says, I would feed in the first half of x, which is really just z in this case. And then I feed it through some function approximator. And then that gives us certain scaling variable. And then I will use that scaling variable to scale each dimension in the other random subset. And then we would, based on that, and then on top of that, we will also shift it. So basically, we are taking half of the random variables, and then we are constructing an affine function based on the first half, and we use that affine function to transform the second half of the random variable. Okay? So that's pretty straightforward, and then we show that you could get a tractable Jacobian determinant, which is what you need to evaluate the likelihood of any data point. And what we didn't cover last time was how do you partition the random variable, right? So you get, like basically you have, let's say in this case, a 4x4 image, and then let's say it's just binary or whatever, but there was no RGB channels in it. Then how do you actually divide this random dimensions basically into two subsets? So, like this is where it needs to have a certain design consideration. So basically the way to think about this is that you want the thing that you are conditioning on the first half of the random variable to transform the second half. So you want these two to have maximal mutual information about each other. So if you condition on the first half, but then the first half knows nothing about the second half, then your transformation is not going to be that meaningful. And so in RealNVP, they propose two patterns. One pattern is what they call a checkerboard patterns. And what they do here is they partition the random variables into called white pixels and then black pixels. So basically, all these white pixels that you see here belong to random variable group 1. So 1, 5, 1, 5, let's call it group A. This thing all belongs to group A. So basically, when you do a feed forward with this layer, you will just copy everything in the white pixel and do not modify it. And then for everything in the black pixels, what you do is you have a convolution map that operates on all the white pixels, and then they give you an affine transformation for each of the black pixels. So you're going to condition on the white pixels and then transform the black pixels. Yes? Yeah. So the right side is another partitioning pattern. So the left side is what they call checkerboard. Oh. And then the right side, I don't remember what they call it, like channel split or something like that. So the other side is I don't actually want to cover this because this is actually not that useful. Like if you actually remove this, the model would also just work fine. But this is in the original paper, which they basically what they said is so the left side is one way to partition the random variables, and then what they actually do is they would alternate. So basically, in the first layer, you would condition on the white pixels and then transform the black pixels. And then in the second layers, you would condition on the black pixels and then transform the white pixels. And then they will alternate to get more expressivity. The reason you do that is if you don't do that, then what you get is basically half of the image is just random Gaussian, and then the other half are some transformation based on, just like independent Gaussian transformation depending on the first half. So that you cannot get much expressivity out of it. And then they also propose another kind of partitioning pattern, in which case they actually shrink the spatial dimension of the image. So what they do here is, if we take a look at this block, this 1, 2, 3, 4 block, what they do is they tile this spatial block channel-wise. So now 1 becomes here, 2 becomes here, 3 becomes here, 4 becomes here. So you're basically shrinking the size, the spatial size, to exchange for more dimensions. And this is presumably useful in some neural nets because now you can have convolution that operates on more channels but a smaller spatial dimension. But you can actually you can actually use deeper networks, in which case you don't even need to use this kind of channel split. But basically, these are the two ways that the paper proposed to do this kind of variable partition, but this is by no means the only way to do it. So one very interesting avenue of research would be to figure out what is actually the optimal way to do it, because this kind of hand design pattern would not capture the real world statistics, and we will see that later, where you will see flow model do not achieve state of the art as autoregressive models. Questions on this? So these are some of the samples from RealNVP, and what you can see is that they can learn some sensible faces and some semi-reasonable outdoor scenes. And what that tells us is that it can learn some patterns in the data, but not to a degree that is as well as, say, some of the autoregressive models that we have seen. And we will look at some of the ways to address this. Let's see. So RealNVP is somewhat magical in the sense that you kind of partition your dimensions into two subsets, and then you say condition on one, transform the other, and now you get an invertible transformation. But why is that the case? Where does that come from? So in fact, that kind of ordering, that kind of invertibility comes from a more general property of BaseNet. So if we have a set of random variables and then we construct a BaseNet structure out of them, then we can construct the flow from the DAG structure of the BaseNet. And this is somewhat abstract, so we will see a couple specific examples that we are very familiar with. So the first one is just autoregressive flow. So what it means is that we have an autoregressive BaseNet structure. So let's just draw it. So let's say we have x1, we have x2, we have x3. So what does that mean is that x1 depends on x2, x2 depends on x1, x3 depends on x2, but also depends on x1. So that's basically all it says. And the sort of probabilistic view of it is on the left, where we would say x1 doesn't depend on anything, and then x2 depends on its parent, which is x1, and then x3 depends on its parents, which are x1 and x2. And that would become the structure of your flow. So basically, you can see that x1 here only depends on z1. It does not depend on any other dimension. And then x2 here would be a function that's applied to z2, which is some entropy source. Oops. But then that invertible function itself is parameterized by x1. So meaning if I give it a different x1, it would apply a different function to z2. So as a specific example, let's say x1 can only take up two values, 0 or 1. Then what we can say is that like this specific function can equals to z2 plus 1 if x1 is 0. Or it could equals to z2 like minus 2 if x1 is 1. So basically, now we have a dependency on x1 because the function that transforms z2 is now dependent on x1. And this can continue. You can have another function that is applied to z3 that results in x3. And that function itself is parameterized by x1 and x2. So what that means is that x1 and x2 influences how the random variable x3 is sampled. So this would be called an autoregressive flow. And by construction here, like because all of the f that we choose here, each one of them is an invertible function. So it would be trivial to invert this thing. And we will show in the next slide. So to invert this thing, remember that x1 comes from applying an invertible function to z1. So when I give you an x1, if I want to map it back to z space, I can just apply the inverse of that function. Yes? Right, so it could be anything. So I mean, we can call z is sample from a Gaussian, but really it could be any random variables. That's coming from the property that you can stack a bunch of flows. So basically, we are looking at one layer of the flow, but what's coming into it and what's coming out of it, like, could be really anything. Could be any random variable. So even though we are only looking at like one autoregressive flow here, you can apply it again and again and again. Yes.
On this slide, is there a reason? Sorry, on the previous slide.
Previous slide.
Is there a reason why we say x3 is parameterized with p theta for only x3 given x1 and not x3 given x2?
Sorry, can you say the question again?
We have x3 given x1, and then just x2, not x3 given x2.
Which place are you talking about?
On the left side.
On the left side? Yeah. Yeah.
X3 given x1, x2.
Yeah.
Why is it x3 given x1 and just x2, not like, for example, x2 and then x3 given, x3 given x2 and then x1?
So I don't quite understand so let me say, like on this side, like it does not condition on anything because it has no parent in its space net. So this one, the parent is x1. And in this case, the parent is x1 and x2. So both of them influence this random variable. Was that the question? Or?
Sure, yeah.
Okay. So right now we're just going through an exercise of if you have z, we know how do you map to x. Then mapping it from x to z is also something that's relatively straightforward. So as we were saying, this is the generation path, let's call it. So basically this means going from z to x. And let's call this is the inference path, which just means going from x to z. Just to show that we can go from z to x and x to z such that the construction is invertible. And the way that you invert the first one is very simple. The first one is just a univariate invertible transformation. So to get back from x1 to z1, you just apply the inverse of that function. Right, so what you obtain now is you get back z1. And then what you can do now is you can say, how can I get back z2 from x2? And then you look at the dependency of this function. This function says, I'm an invertible function that is parameterized by x1. And in the inference path, you would say that I already have x1. So I can actually compute this thing in parallel with z1. So I can compute the result of z2 concurrently with z1. And similarly, for getting back z3, you would say this invertible function is parameterized by x1 and x2, and I already have those because those are the input to me. Then I can also construct that and then just apply the inverse of that function, and now I can get back z1, z2, z3. So now we have shown that this construction is an invertible one. Questions? Yeah, good question. So let's say we only use this, let's actually say Z sample from some standard Gaussian. And then we want to say, we want to fit X, basically. We have some data distribution, and then we want to fit X. And then the way that you evaluate that is by exactly this. So this is my model, and my model is exactly specified by this. So basically, I have a flow that defines an invertible transformation between a known noise space, in this case Gaussian, to some observation space, which we are trying to estimate at this moment. And the way that you do that estimation is by applying change of variable formula, which means you evaluate P of Z, and the Z is obtained from applying the invertible function. So basically, for any data point that you want to evaluate, you map it back to the noise space. Because in the noise space is a unique Gaussian, you can evaluate that, right? So if I give you any Z, you can evaluate this quantity, right? It's just evaluating the density function of a normal distribution. So that's easy. And what else do we need is this determinant term that basically measures how the space contract and expand, and which is given by the determinant of the Jacobian. Yes?
What's the advantage of having like the encoding and decoding done by flows rather than just thinking about the variation element?
So it's somewhat different. We will talk about VAE a little bit, probably in an hour. But basically, the difference here is that in a flow, everything is fully specified. So if I give you a random variable X, there's no other entropy to explain. You fully determine the Z space. Basically, there's no extra random source. You can think of it that way. And in most latent variable model like VAE, you have some unobserved variable that you would never know. You can guess what they are, but you would never, basically there's some extra random source that is not in your observation space. So these are actually two different class of models. Yeah. Right. So during training time, that's a good question. So during training time, what we would do is we would sample a bunch of X from our data, right? And then we would just maximize the log likelihood of this. So during the inference time, actually, we would only use this path. We would not use the generative path at all. So this is basically the thing that we are trying to talk about here. So if we just want to evaluate the log likelihood, then it has the same structure as the autoregressive model that we have talked about. Essentially, you can parallelize all the computation, and then you can get a log likelihood evaluation. And when you actually try to sample it, it would become slower. When you try to sample it, you would realize that the first invertible function doesn't depend on anything. The second invertible function actually depends on x1. So meaning I need to first evaluate 1 in order to start evaluating 2. And then for the last random variable, you notice that it depends on the results of all previous computations. So then the sampling path of an autoregressive flow would be slow, because then you need to do it sequentially. And this is really just a mirror of what we have seen for the discrete autoregressive model, where the inference is all parallelized and the sampling is all done sequentially per dimension. There was a question somewhere. Yes?
Would there be a way to kind of flip it so that inference would have to be done?
Yeah, this is the next slide. So that's a very good question. So this does not make much sense in the discrete case, but it actually makes more sense in a continuous case. So now we have this really interesting class of model. Like you're saying, likelihood evaluation inference is super fast, but then sampling is really slow. But can we actually flip it around and get another paradigm? So it's actually possible. So let's walk through how the sampling is done. So again, this is sampling or generation. And then this is inference or likelihood evaluation. Right, so let's take a look at the sampling path first. So again, oops, I think I messed it. So this should be the generation. So let's look at how does it sample. So the way that it samples now is different. So the first one is still the same. So you would say, I get some random variable z1, and then I map it to some invertible function, and I get x1. But then the next one becomes interesting. You would say, again, my next one is an invertible function that's parameterized by another random source. But now it's no longer depending on x1. Now this function is parameterized by z1, which you have from the beginning. And then similarly, you would say that the way that I sample random variable x3 is by conditioning on z1 and z2. So that you essentially can parallelize computation of all of this at the same time. So if we draw the dependency map, it would look something like this. Z1, Z2, Z3. So basically, X1 is only dependent on this. And then X2 is dependent on X1 and Z2. And then X3 is dependent on X3 and then all previous random variable. So basically now you have sort of inverted the structure of an autoregressive flow. So now what you have is you have a thing that sampled in parallel, but inference becomes slow because all the invertible functions are now parameterized by random variables that are in the noise space. So now you need to recover each of the noise space when you do inference. Yes. Yes, so this means it's practically impossible to train this model. But there's a caveat. So what do you mean by training a model, right? So let's say I give you a bunch of data. In all models like this, you have a distribution that's specified by your model. And then you have some target distribution that you want to get close to. Right. So the typical way that we do that is we say we want to minimize the KL divergence between data distribution and our model. Right. So this is also just maximum likelihood. And then the way that you do that is you say I maximize a bunch of data that's sampled from data distribution and then maximize log likelihood under my model. Right. So basically, all you do, this is MLE. So basically, all you do in maximum likelihood is to do likelihood evaluation. Like basically, the nature gives you a bunch of data points, and now you need to evaluate how likely your model thinks of those data points. So in those cases, like autoregressive flow is absolute trash. Like because to evaluate each of the model, like to evaluate each data point, you need to do basically all of the evaluations instead of everything parallelized. But I would argue like this is not the. So there was actually a case where this becomes interesting. The case it becomes interesting is when the divergence that you try to minimize is flipped to be the other way, then this becomes interesting. Has anyone here tried to do this? So basically now your model is the first distribution in a KL divergence. And we know that KL divergence is not symmetric. So the meaning is different if you put it in the first argument. Has anyone tried this? Like basically have your distribution that you try, have the model distribution to be the first argument in KL divergence. Yeah, so like it's really, like this is what variational inference would do. So like in fact, like inverse autoregressive flow was first proposed in an VAE context where they actually use this thing to fit a posterior. So this is just like a glimpse into what we were going to talk about next. But so basically what this means is that like for maximum likelihood, this is not really useful, but for some other cases, it could be useful. And we will unpack this equation a little bit later in next lecture. So essentially, don't think of this model as like one is absolutely the best or the other is absolutely useless. So there are more of like models that gives you different trade-offs and characteristics. And then it's up to you to use it in its appropriate scenarios. Any more questions on autoregressive or inverse autoregressive flows? And then one more practical note, like when people actually use this kind of flows in practice, like you don't just use one of them. So you don't just use one layer of autoregressive flow. You usually stack multiple layers of autoregressive flow. And the reason you can do that is because each flow is invertible. So no matter how many you stack them, they will still continue to be invertible and a valid probability model. And some other practical trick includes, so for any autoregressive flow or inverse autoregressive flow, you pick an ordering. And people can usually switch those ordering around between each flow. So you capture different dependencies. Cool. So just recap, autoregressive flow, very fast at evaluating probability density at any arbitrary x, but it's really slow at sampling. And inverse autoregressive flow is sort of the opposite of that kind of model. It is where you get fast sampling, and then you also get fast log likelihood evaluation for the samples that you get, but really slow evaluation for an arbitrary data point. And in fact, there are models that exploit this kind of fast sampling to achieve the performance that they need. So one of them is the parallel WaveNet paper. So WaveNet was an autoregressive model, and that was too slow to be practical to use in practice. So the WaveNet author actually changed it to an inverse autoregressive flow and then fit it differently to get a fast sampling. Yes?
Why is it faster than the
Can you say that again?
So in the third point of the inverse autoregressive,
Yeah.
why is it slower for arbitrariness but faster?
Right. So the question is, it's a good question. So the question is this. The first two point is easy to understand, like slow to evaluate, fast to sample. But then like, why do we get log likelihood for free if I sample it? And the core reason is really, coming back to this sampling slides. If we sample, this path, then what that means is that we also know order Z. because sampling procedure includes first sample a Z in your noise space and then feed it through the model. So that means you know your Z. And if you know your Z, you can do this evaluation very quickly. And then you can keep track of all the determinant terms when you are doing your feed-forward pass. So that's why when you do a sample, you also get a likelihood evaluation for free. And the core reason of why arbitrary evaluation is slow is because you need to invert it to get back the Z. So the core reason is like inverting to get the Z is slow, but when you sample it, you have the Z already. Yes. 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 So the question was like, when I do sampling in inverse autoregressive model, do I just sample some noise from my base distribution and then like all the observation space X is simultaneously determined? And the answer is yes.
I think it's worth mentioning that the log determinant of one direction of the flow is the negative log determinant of the other direction of the determinant. So that's also why you can do fast evaluation of the effects of the sample.
Cool. So, so these constructions follow the basenet structures, and not just the autoregressive structure. So we saw that autoregressive structure specify a certain ordering of how those, basically coupling dependencies come together. Right? So a real MVP at its core is really just doing the following, right? So I have a certain set of random variable, and then those random variable is being transformed by a linear function. So Z is my noise space, and then Z is getting multiplied by some A, and then offset by some B. And then, like, how is this affine transformation determined? It's basically depending on all of its parent of X. So if we go back to the example of if we have a 2x2 pixel, and then we use the checkerboard pattern. So let's name this 1, 2, 3, 4, and just color this. So basically what we would have is, like when we condition on the black pixels, meaning x2 is just equals z2, and then x3 is just equals z3. Then what it means is really x2 and x3 doesn't depend on anything. So in a basenet structure, it's just free hanging. And what you have is x1 depends on, x1 is a linear function that is parameterized by essentially a function that takes in x2 and x3 plus another function. So I'm just trying to rewrite this equation. And then similarly for x4, random variable z4 is transformed by some function that is specified by x2 and x3 plus. And these two functions need not be the same. I just draw them to be the same here. So basically what this means is that the basenet structure looks like the following. This is x1. This is x4. So basically both x2 and x3 can inference x1 as specified by the dependency. And then also x2 and x3 can also inference x4. So this would be the basenet structure that's behind a real MVP. And then you just somewhat arbitrarily pick that pattern, and then that gives you an invertible transformation that specify how the dependency for your invertible functions are parameterized. And similarly, you can think of other basenet structure, and then you can write down similar invertible transformation based on this. So we have talked about a couple different kinds of dependencies. So basically, we have talked about an autoregressive base net, and then we have talked about a RealNVP base net. And those basically specify this graph. Like it tells you how are different variables dependent on each other. So really the more general choice is the following. Like for each dimension xi, it's coming from some noise source zi, and then it's going to be transformed by some invertible function that itself is parameterized by all of this random variable's parent. So a different base net basically gives you different structure, like basically gives you different parents here for different dimension. But what we have not talked a lot about is like what is the function class that you can choose for this transformation. So we have looked at things that are basically mostly just affine transformation. So you're saying I have some, it really just linear transformation. You have some random variable zi, and then I'm going to scale it by some scaling term, and then I'm going to offset it by something. So this is a simple linear function that is invertible. But really, like it turned out to be limiting if we only use linear function as the transformation function. So we are getting into like fairly new research areas. Like all of the methods that's listed below are methods that are a couple months old. So this is a very, very active areas of research. And I'm not going to go into the details of how you can choose different f, but essentially think of it as like any 1D invertible transformation that you can effectively parameterize. You can use it as a function of your choice to replace the linear transformation. So some of the choices include you could use the CDF and inverse CDF of probabilistic distributions, like mixture of Gaussians or mixture of logistics, so you can get multimodal behavior. Or you could even just be like piecewise linear function that is invertible, or piecewise quadratic function that is invertible. So we will have paper references at the end of this too. Yes. So that's a good question. So, like, I mean, throughout deep learning, people have been throwing neural nets at everything. Why don't we just use a complex neural net to represent the F here? So it can be as complex as it can be. So, couple of things. Mainly there are two criteria. One is you want to be able to invert it. Like, not all neural nets are representing invertible functions. And then the other thing is you also need to be able to calculate, like when you apply this whole flow, you need to be able to calculate its determinant effectively. So you need to get its Jacobian or similar terms. So that's the constraint. So, but there are actually papers that are looking into what kind of regularization you can put on typical neural nets that make them semi-invertible. We'll also link some of those papers as well. Yes?
But the second question, easier and easier don't need to be invertible.
Which one?
Easier, or A and B. Like
Oh, I mean, if this is always positive and this is whatever, then it's always invertible, right? Right. I mean, so the crucial thing is you don't need to invert back to the parent. You just need to invert between x and z. So basically, as long as A is not, say, 0, then you can always invert it. So that is the somewhat mind-twisting part. Like, now your neural net is not directly outputting your result. Your neural net is outputting a function that is going to transform your results. And you want the neural net to output a function that is invertible. So basically, that's the design challenge. Like, what are other things that your neural net can output such that it parameterizes an invertible function? And the reason, like we mentioned, like mixture of Gaussian and mixture of logistics is because those are things that are easy to represent. Like your neural net can output a bunch of mixing weights, and then the mean and standard deviation of each of those Gaussians, then now you automatically get an invertible mapping. Not everything is easy to evaluate though. Like say, mix of Gaussians is actually fairly nasty to use in practice. But the nice thing about this is that like for all of those, we, like sometimes we find invertible function like very hard to approach and like very hard to compute, but it's actually not the case here because for everything that we're talking about here, the invertible function is only 1D. So if you say no certain thing is monotonic, even if you cannot analytically invert it, then you can do bisection. And it's not the end of the world to do that. Cool. So this is talking about, so basically, as I said, this is a fairly new class of model. So RealNVP is only 3 years old. And some of the other classes of models that we will see are, like some of them are a couple months old. And they are not really at the level of some of the state-of-the-art method like autoregressive models, but it's rapidly advancing. So part of what we want to have this class to convey what are some of the directions that you can possibly pursue to improve this kind of model. So this one we have talked about one that is like the choice of the transformation function matters. And then the other thing is the neural net architecture also matters. So generative model, not like in vision where people have already spent a lot of efforts on figuring out what is the right neural net architectures to represent those models. Like there's still fairly limited research to figure out like what is the right neural net architecture to use. So in a lot of cases, like the model performance could also just be bottlenecked by the neural net that you choose. So the specific example that we give here is essentially we're going to compare models that use affine coupling, so basically the linear transformation that we talk about, versus a mixture of logistics coupling. So these are the performance difference that it has for a half-trained model. So this is called like the function choice matters. And then this is where we compare a model that has self-attention versus a model that purely only has convolution. And then again, you can see a performance difference in there. And this is like not mean to say that you should definitely use self-attention in all of your generative models. And this is also not to say that you should definitely use mixture of logistics in this kind of models. But it's really meant to illustrate that like those are the dimensions where you could trick the models. You don't need to take them wholesale as is. Like there are dimensions that you can change to suit your problem better. So let's see. So there are some other classes of flows that we have not covered here. Probably the most popular one of them is called GLOW. How many people have seen GLOW and its results? So not everyone. So GLOW is a recent generative model that is essentially adding two core components to RealNVP. One is they have a 1-by-1 invertible convolution. So this is, well, not really convolution. You just apply an invertible linear function to each of the pixel location. And, well, because it's an invertible linear function, you can invert that fairly easy. Well, with some effort, not fairly easily. And then what they also do is they did some very large scale training on high resolution images. But then the results that they get were really good. So the pictures on the right are samples from the model with some temperature control. So if you have not seen it, then we should look at the results a little bit. So what's something pretty interesting is that after they train these models, some of the noise variables take on semantic meaning. So what that means is that like you have this 200 by 200 image that's mapped to a 200 by 200 latent space. When what they found is that some parts of the latent space actually have meanings. So some of them they name, say, smiling. So this is, on the left is the input image, and on the right is the output image if you trick this neuron. So let's say we minimize smiling, then you will get a face that is not smiling. So can anyone tell me like what was happening there from a flow standpoint? Right, so you map the left image, which is in X space, map it to Z, and then you tune one of the knob of the Z, and then you map it back. So then we are basically visualizing like how if you change some part of your noise space, like what are the effects on the data space. So and then you can see it, you can make it smiling. And you can see that it's not perfectly decoupled. Like smiling is definitely somewhat also coupled with the lighting. Maybe people in poor lighting tend to be unhappy. I don't know. And we can tune age as well. Again, like this is not perfect abstraction. Like I mean, I'm not sure if this is still the same person anymore. But still, it gives you a sense that like this model can actually learn meaningful semantic structures in a fully unsupervised manner. And then you can try different faces. That's cool. I actually like this one better. This one's really artistic. Okay. Anyways. So flow models can be adapted, especially when trained on large scale and with specialized sampling techniques, can be tuned to make good quality samples. And there are some other ways to construct flows that can use more unrestricted neural net architectures and things like that. We will link some of those in the end of the lecture. So one more note on flow. Flow is really a generalization of the autoregressive, discrete autoregressive models that we have seen. So for the discrete autoregressive models, what is actually happening is you take some image in observation space X space, and then you map it to Z. But then in this case, the Z is basically the index of the inverse of CDF of each of the conditional. So it's similarly, you're just inverting everything back into noise space. But the crucial difference is in discrete models, you will not be able to stack layers on top of layers. At least I don't think anyone in the community knows how to do that yet. If we know, then like that would be a pretty big breakthrough. So that's it on different construction. Yes.
So can you explain again why you can't stack layers?
I guess how? Like I don't know how to do it. So yeah, I'm not sure like how. Maybe the best way to answer the question is try to stack it yourself and then find out that you cannot stack it, or you find out a way to stack it, then that would be great. Yes.
So you have a Z for each X.
Yeah.
So it's not really like a dimensionality reduction.
There's no dimensionality reduction.
You can't really interpret that as a latent space either.
So this is the funny thing, right? So this is so the question was, there's no dimensionality reduction, right? So your input is d-dimensional. You map it to your latent space, well, call it latent space or noise space, and it's still d-dimensional. Like, so this is really go in contrast with the sort of classical way of thinking about representation learning. The classical way is like PCA, ICA, like where you say, find me the most important dimensions in your data, and then only capture those. Like, this is completely different. This is like, I preserve all the same dimensions, like in both discrete models and flow model. You preserve all the dimensions, and then you just evaluate a likelihood. Like, so this is like somewhat absurd from a traditional representation learning standpoint. And then people also like are saying, like, what do this noise really learn anyways? And I think the GLOW model is a very good example. Like, so we don't really know why it learns semantic features. Like, there's no strong reasons that it should learn semantic features. But they do tend to learn certain meaningful knob one way or the other. It's similar to the unsupervised neuron, unsupervised sentiment neuron detector, where they train an INN on a bunch of text, and then one of the hidden neuron happens to correspond well with sentiment. Like, so maybe it has something to do with the way that we construct the neural network, so that it would make the neural nets drop easier if some of the dimensions have certain meaningful influence on the others. But like, really, that's something that we don't really know. Like, why does Glow learn semantic features? We don't know. Like, yes.
It could be because we are trying to. Let's say we're using like uniform random samples, right?
Yeah.
Then we would expect our noise samples to be each other.
Yeah.
And one way to do it is to do this example smile. For example.
Yeah. So well, this is not really a question, but an answer to the question is, so let's say we use independent Gaussian as our random noise. Then basically we are saying each of the dimension in my noise space should be independent of each other. So maybe a good way for the neural net to represent something is to say each of the dimension represents some disentangled factors of variations that are present in your data. So I think that's a good hypothesis, but we have no way to know whether it's actually doing that.
So if you view it as like your input is an image, and then you fixate yourself on one of these, and you just change one of these.
Yeah.
Is that going to?
So that was what was being shown. So in the link, in this demo, this is exactly what's being shown. So you map an image to Z space, and then you keep everything else as fixed, and then you just change one of them. And then see what they do. Yeah, even though there are thousands of random variables. So I mean, there are places that you can like you can construct your neural net to make certain variables more important. So there are ways that you can do that. So style GAN, like which we would capture when we do the GAN lecture, is a very clever way to do that. It's by saying some set of your random noise need to contribute strongly to certain way that the data is generated. Then you can kind of guide it into a certain direction, but again, still it's not guaranteed that it would do what you want it to do. Cool. So we have talked about flows for quite a bit. And what we have been talking about is essentially always assuming we're trying to fit some continuous variables. So we have some continuous data source that we're trying to fit, and flow models would be one way to fit them. But that's not quite true in practice. And in most actual data that we get, they are quantized data, whether you want it or not. Like, I mean, you get them in floating point, so they are quantized already. So there's one issue of applying, just say, blindly applying flow to discrete data. So let's say my data are just some 3 big pixel values, so it goes from 0 to 255. Then, like, there's a question of, like, what does your model, like, what density do you assign to values that are between bins? Like, let's say I'm trying to query my model on values like 0.4. This is valid because I'm learning a continuous probabilistic model, and I can query it for 0.4. But, like, what should it output? Like, should it just output 0? Because, like, there's no data that it observes that are on, like, a fractional value. And in practice, like, what happens is that, let's say this is 0, this is 1. Oops. Let's say this is 0, this is 1. And so what happens is that if you evaluate, like if you fit a density model, and if you only fit it like 0 and 1, what happens is that it would have a tiny spike that's only centered around the discrete values that you make it see. And then in fact, you can make that value infinitely large. And that would not be, basically the model can cheat and have really good log likelihood score without actually learning the data well. And the correct thing to do is really want to have a continuous distributions. Let's say this is 0, this is 1, this is 2. What I really want is I want the cumulative probability mass in, say, between 0 and 1 to correspond to the actual, call it empirical discrete probability mass. Like, what are the actual values that we are going to get that all get beam to 0? So if we write it out, like, let's say this is our favorite flow model, like whatever that is. And what we are going to do is that we're going to say what we actually care about is a probability model with capital P that just denote, right now we are worrying about discrete values now. So X, this can take a value of 1 of 0 to 255, but not 1 in the middle. And then we'll say that, like, essentially this is the real model that I care about. And then the real model is defined by how much probability mass falls under that unit cube in this case. So far, so good. So this would basically correspond to like a histogram. Like originally we would count, like we would have histogram that just say how much probability mass falls under each beam. But right now we no longer have a histogram. Like right now we get a bunch of continuous density. So we need to define like what we mean by probability mass, and what we mean by that is just the integral of the probability mass in between them, or of the density. So then the solution to actually fit a continuous density model with discrete data is called dequantization. So basically we turn it back into a continuous variable. And what it really means is just that you add noise to the data. So let's say my data goes from 0 to 255 in integers, and what I would do is I would sample random noise uniformly from this unit cube, and then I would just fit my model to this thing. So basically the way that the fitting works is I sample one data point from nature, and then I would sample another random U, and then I add these two things together. And then now I force my flow model to learn X plus U. Does this seem reasonable? Yes.
If our data is actually categorical, it doesn't get us anywhere, right? Like if it's not like discrete values that are pixel, but like, I don't know, my gender or something.
Yeah, so like basically one can argue that like you might not want to use continuous model to fit that anyways, but this can still allow you to fit it. Like you can still count the probability mass under this model, but you can say, like basically what I'm saying here is like this is pixel value 0, this is pixel value 1, and they have some semantic meaning, so like you can see that why it needs to be somewhat continuous. But this could well be like, I don't know, your political party, like Republican, Democrat, then like it basically means nothing. But still, like you can still do it. Like you can still fit it the way that it is. Yes. Yeah, so good question. So this is what's being shown here. So in fact, people started adding this kind of noise because they found out that they could not properly evaluate their model. So if they don't add some continuous noise to their model would just cheat, and then they wouldn't get any meaningful measure. So probably starting in 2013, like people started adding this kind of random noise to their model to evaluate the continuous models. But like for a long time, people actually didn't know what does that precisely mean until probably a paper in 2015 that says it actually means something when you do this. So basically what we have proposed is we say, instead of fitting X, which is discrete directly, I'm going to fit Y, which is discrete value plus some continuous noise. And then what we are going to show next is that when you fit this constructed Y random variable, you're actually fitting the lower bound of the capital P model, discrete model that you care about. So the rough way that it goes is pretty simple, like it's just applying Jensen's inequality. So this is how we get our data. So this is from X from data, and then U from uniform, and then you just like add these two together. So now we know how to sample Y. And then we also know how to evaluate what's inside here. Like we get any Y, and then we just map through our flow, and then we get some noise variable, and then we multiply that by the determinant of Jacobian. All of those are fairly doable. Then if we write out what does this mean, it means the following. So we first notice that X is sampled from some Mother Nature X distribution. And then you're going to sample uniformly in this unit cube, and then evaluate that log likelihood under your model. So basically, at this point, what you can do is you can just apply Jensen's inequality, and then you pull the log out of the integral, and then you get a lower bound of this thing. And then if we squint at this quantity, this is precisely how we define the probability mass that falls under that unit cube. So essentially what this says is that by this kind of construction, I get some new random variable Y, and when I fit it, and when I evaluate the log likelihood under that noise distribution Y, I actually get a lower bound of the true probability that I care about. So including, I can use this to fit a fundamentally categorical distribution, and it will give me a lower bound of what the true discrete probability is representing. Cool. So now we can use flow in actual data. Some comments on relationship to compression. So maximum likelihood for densities is really kind of like you're coding with very fine discretization. So you're saying like each of my bean is really, really small to a degree that is well approximated by the density. And what about non-infinitesimal discretization? I actually have no idea what does this mean. You need to ask Jonathan that. Do you want to explain what does that mean? Later. Okay, sounds good. So far we have talked about two classes of what we call exact likelihood model. So we have discrete autoregressive models, and then we also have flows. So both of them are exact likelihood model where if I give you a data point, you can tell me what's the prescribed likelihood. The nice thing about this kind of model is that the training is usually stable. Like, I hope that's your experience in your homework one. Like, you don't get crazy oscillations or crash like you would get from GAN. Okay. It doesn't seem very reassuring from your facial expressions. You should contrast that with your GAN homework. You would appreciate. You will appreciate now. But so like it has some nice properties of like being stable in training, like has good probabilistic interpretations and whatnot. But they are not perfect. Like you see that you can get some good samples sometimes, but not always. Like what are the good principles that we can use to do that? And then you see autoregressive models that are very fast, that have very fast inference, fast to train, but then like very slow to sample, making them kind of useless if you want to actually sample from them. And also, probabilistic models like capture patterns in your data. Like how can you turn those patterns into actual compression algorithm to make it possible to transmit fewer bits? Like all of those things are, like we have given some answers in these two lectures, but really they are really vast open fields that have a lot of potential that are still untapped. And yeah, so that would be, I think last slide of flow. Any more questions on flow before we move on?
So there's no way to like train an autoregressive flow so that we train it quickly, and then
You can train it quickly.
and then
Autoregressive.
invert it after we train it quickly.
Yeah.
Like give the structure.
Yeah. So the question is, so we know autoregressive model can train quickly, but does not sample quickly. But can we somehow make use of it such that, like, we first train it and then we somehow convert it into a fastest to sample form? So I think a couple people have tried this. So like basically you use a AF to learn the data, and then you use an IAF to imitate that learned network. So there are some possibilities along those lines. But I don't think there are like known best practices for things like those.
Because you mentioned that like the Z and the IAF is just it can be any like distribution, any noise.
Yeah.
So why can't and in next layers of the flow,
Yeah.
the Z is just the output of some previous flow.
Yeah.
So why can't you just have an AF that then links into
And IAF?
yeah.
Then you get the worst of both worlds.
That's
Because you get slow training and slow sampling. Yes. Yeah. Yeah. Yeah, so the question was, like, what if the data that you care about is inherently very high dimensional? So high dimensional that you are very sure a bunch of them are redundancies. And you really want to find a representation that is lower dimensional. So in RealNVP paper, we didn't go into that detail, but they had something like that. So I encourage you to read that paper. Essentially what they do in that paper is they apply different depth of transformations. So I have some high dimensional X, and then I map it through a couple layers. You get back the same dimension of Z. Right? So you can think of like you are iteratively Gaussianizing the distribution, because in the end you should map it back to a Gaussian to get perfect likelihood. So you can think of like each layer that you apply is Gaussianized a little bit. Then what you can say is that like I would, for certain random variable, like for certain dimensions, I would stop processing them. So let's say after I apply 3 layers, there are a bunch of them I would just keep fixed, and then the others I keep processing. Then those would be heuristics that you can use to say, oh, then those things that stop processing earlier should capture the simple patterns that are already Gaussianized in the first couple layers. So there are heuristics that you can do with that. So basically those tie back into the neural net architecture design question. Like that is what kind of inductive bias you can build into your neural net to make it create the kind of latent code that you want it to create. Yes? So discrete flow is basically discrete autoregressive model. So that's one way to do it. And otherwise, like, I'm not sure I get the question, but otherwise what you would do is you would just dequantize it. You would just add noise to it as you sample the discrete images. Yeah. So basically, I would pick an image, and then I would add some noise to it, and then I'd tell my model to fit it. And I would pick another image. I would add some noise to it, and then tell my model to fit the noise version of the image. Yeah. And that's generally how you give categorical or discrete data to a continuous model. It's by basically making it continuous. Cool. Okay, who's excited about latent variable model? Some people. So what we will cover, what we are going to cover, we are not going to go through all of them today, but we are going to begin to cover another large class of. Okay, so Pieter says we're going to take a quick break, so we will take a break. So let's resume. Hello. Hello, hello. Can I get your attention? So, pizza is not here yet. We will do pizza in the next break. I know that's what you've been thinking about. Come here all for the pizza. What are these lectures? All right, so where were we? Okay. Yes, maybe someone else can post this. Peter, can you post the slide? Cut out the last slide. So we have looked at exact likelihood models where you essentially can evaluate the likelihood of any data point exactly. And this is going into the second large class of models, and it's fairly distinct from the first class in the sense that you would not get exact likelihood evaluations. So it's still likelihood based, but almost in all cases, you don't for sure know what does your model say. What is your model's likelihood for a given data point? You might say why do we want that? So we have looked at autoregressive flows and autoregressive models and flows, and in those cases, you might put some ordering on your random variables and have certain dependencies among them. But really, all the random variables are observed. There are no unobserved variables. So broadly defined as latent variable models are you're facing certain random events, and then part of them you don't get to observe. So let's say in these cases, you get to observe X, but then you don't get to observe Z. So even though X is dependent on Z. And it basically just means, precisely that. So why is this helpful at all? One argument is that if you look at pixel space, this is a pretty high resolution images, probably, 800 by 800 by 3. It's a pretty high dimensional space, but really, oftentimes much simpler and lower dimensional representations exist for the data, and they are not always. They don't capture all the details. Let's say in this case, we can say this image is captured in certain background. This is on a bench in a park, and then you can describe what are the objects that's in this image. So this is a fairly concise and low-dimensional representation of this image. And you can call these are the latent variables of this image. So it would be nice if we can actually describe the data in this format, right? Instead of showing all the bits and for all these high-res images, it would be great if we could get a much simpler latent representation of the data. And then, of course, the latent representation only specify this is a corgi, red and white color, but then there are a lot of details that are unspecified. So that's why you still get some randomness in Z, in X after you determine the Z. So the Z here are just this high-level descriptions. And that would be a great way to do it because now there are some random details that I don't care about that get encapsulated by an observation space model, and then I can get to capture the essential information in the latent space. So why is this useful? It's also useful in the sense that it can simplify your probabilistic models. So autoregressive models are slow to sample because you are assuming all the pixels dependent on everything. Dependent on everything before it. But if we could make part of the observation space independent, condition on some latent variable, then that could drastically speed up the sampling. And then the speeding up of the sampling is really a result of the fact that you exploit certain statistical patterns that are in your data. that are otherwise captured in a very blind way in an autoregressive model. So what does that mean? That means like, let's say if I am given the latent variable model of there's an object at this location, there's an object at this location, there's an object at this location. What I can do is I can sample these three objects independently, condition on the random variable. Because like, if the random variable, if the latent space already described everything about them, like, or the essential interactions about them, then like between two objects, there no longer needs to be dependencies. And this is in contrast with an autoregressive model would say, this pixel needs to depend on like all these other pixels before it. So that would be essentially a way to allow you to capture more patterns and then use those to either speed up inference or speed up sampling. Any questions about that so far? Yeah, I mean, it also speeds up training if you can find the right latent structure. Basically, the way the autoregressive model is designed as is we are saying we make no assumption about the data. Like we know an autoregressive factorization works for all random distribution, but like in practice, the real-world data that we face have a lot more structure in it, and it's not able to exploit those. So sometimes it's possible to design some latent variable model with an understanding of how things are actually generated. So this is sometimes the case in certain scientific processes. You know, like certain particle would have some interaction in some random way, and then causes some observation. But then like you actually know something about the causal generation process, then you can actually specify the latent variable to be something that is physically meaningful. But those are scenarios that are relatively rare. And in most cases, like when we try to model images, videos, audios, protein, all these kind of things, like we actually don't know their underlying generation structure. So you really wouldn't be able to specify like what are the latent variable structures are like. So in practice, like what the most popular models that people tend to use is they have for certain latent variables, but they don't really specify how do those latent variables interact with observation space. And frankly, we don't really know what is the best way to specify latent variable models to get the best out of it. So again, like think of like what we're going to cover as tools and ingredients that you can use instead of like prescribed canonical way to do everything with. And in most cases, like if you know certain problem structure in the problems that you're trying to solve, and then you can come up with a wide way to encode the latent structure in there, then you can usually get a lot of gains. So okay, so let's look at a very, very simple latent variable model. Right. So what we have here is we're going to say we have some Z that we call our latent code or latent space. And this Z is really just a bunch of K binary variables. And then it's distributed according to some parameter beta. It's basically a Bernoulli independent Bernoulli distribution parameterized by some coefficient beta. Okay, so now we know how to generate Z and how to evaluate likelihood of Z. So far, so good. And then what we are going to say is the observation space is also binary random variables. And there are L of them. And what we are going to say here is that I don't specify what is the distribution of P of X. So this is implicitly defined. What I explicitly define is this quantity. I give you a probability distribution that prescribes what is X given Z. So now I have sampled a random latent variable. So this is a binary strings. And this binary strings would fit into a deep network or really any other kind of function approximator. And the output of that function approximator is some some coefficients that parameterize the Bernoulli distribution of xi, of observation space X. So far so good. So let's say, when you can say, how do we generate something from this model, right? The generation path is I first sample Z from this P of Z. This we know how to do. We're just sampling some independent Bernoulli distributions with some coefficients specified. So we know how to do that. And then after we get Z, we would map Z through some network. That gives me another chunk of parameters. Call it like 0.1, 0.2, 0.9. Let's say L is 3. Right? So the network gives me another set of parameters. And this set of parameters, I can use them to generate X. Right? So now I generate X from P of X given Z. And really, this is just a Bernoulli distribution that's parameterized by the probabilities described here. So let's say I sample a bunch of things, call it 0, 0, 1. Most likely outcome. So now we have a probability distribution, and we know how to sample from it. So far, so good. So what are the parameters that we can train? So the parameters that we can train are, these deep networks have some parameters, and then beta are also parameters that we can train. So now we have a probability distribution. Now we want to fit this distribution to the data. So we have parameter data, we have some data, and then we want to fit this. So how are we going to fit this? The way to fit this, again, is by maximum likelihood. So you're given an X, which is a binary string, and then you need to evaluate this binary string's probability under this model. But now you say, like, where do I get this marginal, like P of X? It's actually not explicitly defined. And then the way to actually evaluate it is you need to essentially sum over all the possibility of Z. So I'm going to enumerate all possible binary string of Z, and then that gives me essentially, like I know how to evaluate P of Z, and then I also know how to evaluate P of X given Z. And then if I sum all of this together, that would be my marginal probability. But that has a problem. So the problem is, like, this is not very scalable in how complex your latent space is. Let's say if I have a latent dimension that has a binary string of, that has 32 binary characters, then that's already a summation over 4 billion terms. So this is not very tractable to do. Right, so to recap, what do we have? We have O1 access to P of Z. Like, given any Z, we know how to evaluate its likelihood. And this is usually what we call the prior. So we know how to evaluate the probability of the prior. And then we also know how to evaluate the conditional distribution of X given Z. Then if I want to learn this model efficiently, then what I want is I want to have a way to efficiently compute what we call the marginal, like meaning you marginalize out Z, the marginal of P of X. And we have seen in the last slide that it was challenging due to the intractable sum. All right. So how can we solve this problem, right? So we are stepping into variational inference. And one way to motivate this is you can say, if I have an oracle, let's call this oracle as given this X, what were the distribution of Z that could have generated this? So if I was given this oracle, then I can evaluate marginal fairly trivially. So because marginal is just the joint, so this is equals the joint probability of these two random variable divided by the conditional of z given x. Right, so if I have this, then I can evaluate the marginal likelihood directly. So that would be great. But the problem is you wouldn't really be able to access this quantity, P of z given x, which is what we call true posterior. So what it means here, what does P of z given x means? It means I observe an x, and then I want to find the posterior distribution that have generated this. And what does it mean? It means I would divide the joint by the marginal of x. But then again, marginal of x is something that was intractable. So sort of we are back to step one, where you're trying to evaluate the intractable marginal. That's not so good. And the core idea of the variational inference is really, I have this true posterior that is intractable, z given x, but it's really useful for us to evaluate marginal likelihood. So what we are going to do is we are going to learn a distribution q sub x to try to approximate this. So the reason we parameterize it this way, q sub x, is really this marginal this approximation needs to be different for each data point x, because like a different part of the latent space would have generated it. And then the core challenge is how do you essentially try to make my Q as close to the true posterior as possible. So I think we should take a piece of break. Otherwise, we're going to be cut in the middle of math when you should have pizza. So let's do a 10 minutes pizza break. So for people that are back, how many times have you seen derivations like this? I mean, this is, I think, pretty common graphical models, probabilistic models stuff. How many people have used EM before? Expectation maximization. Wait, really? For those of you who didn't raise hands are not qualified from the class and can now go home. Just kidding. So EM is another way to do like basically inference in latent variable model. It's actually you can derive it as a special case of variational inference that we are learning now. We should have that as a homework exercise. Okay. So where were we before the break? So we have prescribed a certain probabilistic model that has a latent variable z that is unobserved. And then when we need to do inference, we need to sum over all possible z. So that is not quite tractable. And we have mentioned that like if you have a true posterior, meaning P of z given x, then you can do inference very easily. But then the problem is you don't have the true posterior. So the whole idea of variational inference is let's approximate that quantity, and let's see what we get. So right now what we have is we have a true posterior that we do not access, and then we have what we call an approximate posterior that we try to get close to the true posterior. Okay, we call P sub x of z. So this is our approximation, and we try to get close to this. And what do? Well, you pick a certain divergence between two probability distributions, and then try to minimize the divergence. And the choice that we are going to make here is we are going to what's called I projection of Q onto P. So let's bear with the choice for now, even though it's not the most common direction of KL that you will see. And then what we do next is really just write out the definition of KL divergence. So what's on the right here, just expanding the definition of KL divergence. So it means you would sample Z from your approximate distribution, and then within this expectation, you would evaluate log of Q minus log of P of Z given X. Okay, so this is just the definition of KL divergence. And then what we realize is that you can rewrite this conditional as a division of the joint probability divided by the marginal. Again, very basic stuff. And then you can pull log of P out of this fractional. So now what you get is you get an expectation of samples of Z that involves one of the Z term, another Z term, another Z term, and then finally something that does not involve Z, which is the marginal of the data point that you care about. So since this term does not depend on Z, we can just pull it out of the expectation. So far, so good. And what's really interesting here now becomes, if we think about Q of, when we're trying to minimize a distribution of Z, then really, since this term does not depend on Z at all, we can really just ignore this term in maximization, in the minimization of this KL divergence. So actually, this part is the only part that we need to minimize. So what have we done here? What have we done is something that's actually pretty interesting. What you have achieved is you can say, I can have my approximate posterior to get close to the true posterior without evaluating the intractable sum to get the marginal. So that means like I could actually make this two distribution closer without doing any like hugely intractable computation. And so this is an expectation, and then it can be approximated by stochastic samples. So I can draw sample Z from Q, and then I can just use empirical average to approximate the terms that's inside this expectation. And then if we look into the expectation, Q of Z can be computed in O of 1 time. That's just the approximate distribution that you choose. Let's just call it a bunch of factorized Bernoulli distribution. And then you also need to evaluate the prior probability, P of Z, and then also the conditional probability of P of X given Z. So all of these terms are terms that can be evaluated efficiently. So what does this mean is that we can actually come up with an approximate posterior and then steer it towards the true posterior with scalable stochastic optimization without ever doing the intractable sum. So far, so good. So that is good, right? So that means like we have this approximate posterior, and then as it gets close to the true posterior, and then we also know that if my approximate posterior is exactly the true posterior, then I can evaluate marginal likelihood instantly, right? So that is some good sign. But then like you actually get more out of this rearranging of algebra. So this is just restating what we had from last slide. So if you minimize KL divergence from Q to P, and then what you would get is an expectation over terms that you can efficiently compute, efficiently sample, plus the marginal likelihood of X. And what I'm going to do is I'm going to just rearrange all these terms. So if I have my log of P on one side, and then put my expectation to the other side, then what I would get is the marginal of log of P, P of X, would equals some terms. Let's ignore what's inside expectation, and then a KL divergence. So one property that we know is that KL divergence is non-negative. So if KL divergence is 0, then that means these two distributions matches each other exactly. but they are always non-negative. And when two distributions differ from each other, you have positive KL divergence. So what that means is that this term is always positive. And then we have this expectation on the left side plus an always positive term equals the marginal likelihood. And what that means is that the thing on the left is always a lower bound of the marginal likelihood. So now that's some progress. So that means again, this expectation as we have described is a term that we can efficiently compute and approximate. And now what we have shown is that this term is actually a lower bound of the marginal likelihood that you care about. So why is this important? It's important because in maximum likelihood, what you try to maximize is the quantity on the left. And now I have a lower bound of that quantity. And that means if I maximize this lower bound, then I can make progress towards the actual likelihood. And you can say, by knowing that it's a lower bound, then how loose is the bound? What's the gap between my lower bound and the actual marginal value? And that is also known. So let's look at what does this KL divergence mean. This KL divergence essentially mean on the left side is my approximate posterior, and on the right side is the true posterior. So basically, the gap between my lower bound and the true marginal likelihood is exactly the gap of my approximate posterior to true posterior. So this is pretty beautiful. That means you have a bound, and then you also know how loose is your bound. In the semantic sense, that it's not just applying some Jensen's inequality and then not exactly knowing how loose is your bound. And then what we can actually also see is that if you maximize this lower bound, and then let's say you have an infinitely expressive Q, and then you maximize this lower bound, the optimal Q that you achieve would be exactly the true posterior, and in which case the bound is tight, equals to the true likelihood that we discussed before. Questions so far? The silence is unsettling. Yes?
Can you explain again how we know how tight it is? Because we can't really evaluate.
So that was not very precise. So we don't, in practice, we don't really know how tight it is. But we know the gap is exactly how worse, how bad is our approximate posterior.
So how do we know that?
So there are actually ways that you can approximate this, but you can never know for 100% sure. So there are ways that you can, one of the techniques that we mentioned probably in the next lecture is you can use importance sampling to improve your approximate posterior guess. And then the more that importance sampling can improve, that means the larger the gap that exists. Yes?
So you said the gap between the lower bound and the marginal, the gap is same as approximate and actual posterior.
Can you say the question again?
You said the gap from this lower bound and the margin.
Yeah.
Same as the gap between actual and
So basically the gap between the variational lower bound and the marginal is exactly this term. Because in the equation here, there's no inequality. So we know the marginal is exactly equals to the lower bound plus the KL divergence. So basically the KL divergence is exactly the gap. And basically that measures how bad is your approximate posterior. Yes?
So KL divergence can be defined depending on the support of
Right. We assume it's well defined and has condition, all sorts of regularity conditions that satisfy this. So we assume we operate in that region.
Okay, so our variational lower bound is never going to infinity.
Yeah. I mean, it can be, but it's generally you initialize it to be not the case, and then your optimization wouldn't push you into that direction. Yes. Yeah, that's a good question. So essentially the question was like, why do we know that? And the reason we know that is by looking at the first equation. So when we try to minimize the gap between our approximate posterior and the true posterior, which is what this means, right? You try to minimize this. And then when we try to minimize this, on the right-hand side, the marginal does not depend on z at all, so we cannot change that at all. So basically, when we try to maximize this term, the only thing that goes into effect is this negative variational lower bound. So basically, if you maximize variational lower bound, you minimize the negative of it, which is exactly minimizing the gap. So this is kind of restating the objective. Okay, so now there's some progress. Then that means like I can start to fit my model. Like if you give me some data distribution piece of data, and I'm going to draw some samples from it, and then now I can fit my model. The way that I fit my model is you first give me some data from nature, and then based on the data, based on each different data point, I would have a specific approximate posterior guess, because different data points have different posterior. So for each data point, I have a specific Q sub x to approximate that posterior. And then this is just the VLB, the variation lower bound. And now, like, all the terms are terms that we can evaluate. And then if we could maximize this iterative expectations successfully, then we know this expression is a lower bound on the true marginal likelihood that we care about. So presumably we can make some progress. So that's the ideal world. And so far what we have covered is called the core idea of variational inference, which is learn an approximation of the intractable posterior. So in this lecture, what we're going to focus on is it can be used to learn latent variable generative models, but it can actually be used to in a couple other scenarios that we will cover later, but not now. But this is meant to say that like this technique that we're talking about here is not specific to generative models. Like in fact, like in cases where you have unobserved variables, then very likely you can apply variational inference. Okay, so knowing what we know now, let's go back to our simple Bernoulli latent variable model, where you have k of z and they sample from some factorized Bernoulli distribution. And then you also have some neural net that map from the latent space into coefficients of the observation space, which is again a Bernoulli distribution. And now we have this variational lower bound that we know if we maximize can make some progress on the marginal likelihood. So let's try to do that. So let's try to just plug everything in and then walk through what would happen. All right. So now I have let's say this is given a data point x. Let's try to evaluate this. Given data point x, I instantiate a certain approximation to the posterior, and I'm going to draw samples from it. Let's say this is, again, a factorized Bernoulli distribution, so that we could basically have k coefficients that describe where what random variable is more likely to be 1, what is less likely to be 1. And given z that was sampled, then let's evaluate each term, right? So we have the prior term, which is just plugging in this probability mass function, which is easy. And we also need to evaluate the log likelihood under the approximate posterior. So assuming it's a factorized Bernoulli, it's also easy. And then evaluating this term is also easy because you just fit a z, which actually comes from Q. you fit a z through the network, and then now you get coefficients for x. Then you can also evaluate this term pretty effectively. And if we say, okay, so now I want to take a derivative of this objective with respect to its coefficients in order to learn it, then we can see that like it's very straightforward to take derivative with respect to theta, which is just one term in the expectation. It's also very straightforward to take expectation with respect to beta, which is the prior distribution, because it's also another term in the expectation. However, I claim that it's tricky to take derivative with respect to phi, which describe the variational or approximate distribution. Why is that the case? Right, so the core challenge is you are now optimizing an expectation, right? So in most like places where we apply stochastic gradient descent, you have some data, and then you approximate you're optimizing some function that takes in x as well as theta. But now in this case, it's like the input also depends on theta. Like how the distribution is sampled also depends on theta. So this is sometimes known as an expectation maximization, like expectation optimization problem, where you are trying to optimize the distribution under which data is sampled. So let's say, I know a lot of you know how to optimize this. Let's just assume that we don't. And look at methods that's assuming we don't know how to do this. So this, yeah.
In order to evaluate that, how many samples do you
So the question is, like, in order to evaluate this objectives, or approximate this objective successfully, how many samples you need to draw? It depends. It depends on the complexity of your latent space. So in some of the more discrete one, you would need more, because it also depends on how good is your approximate posterior. Like if your approximate posterior is perfect, then like one is enough. If the worse it is, the more you need. So for now, let's assume that we don't know how to optimize expectation, like meaning we need to sample something from a parameterized distribution, and let's say that we don't know how to do that. Then what people have been doing in the past is to look at ways that circumvent that problem, right? So if we look at the core of the problem is really the sampling distribution here also depends on, the sampling distribution here is exactly your approximate posterior. So you need to sample from your approximate posterior. And as such, you need to optimize that expectation. So what people have looked into in the past is say, can I get some samples that are not from my approximate posterior? So if you do KL in the direction of Q to P, then you're going to sample from Q. Then what if you say, let's try to minimize the KL divergence from true posterior to Q? Then now you're sampling from true posterior as opposed to your approximate posterior. Then you can essentially circumvent the problem of optimizing expectation, because now the expectation is under something that doesn't depend on Q. So, but there was a problem, right? So we still don't know the true posterior. Like if we knew it, then like we wouldn't need to optimize for it. So the core problem is, how can we do that? And really the core trick in what's called wake-slip algorithm is an algorithm that's like 3 decades old. The core trick in this algorithm is by saying, if I generate the data myself, then I know what Z generated X. Right? So let's say I know how to sample Z from my latent code, from my prior distribution. And then I also know how to sample X from my conditional model. So both are easy. Then if I give you X, then I know which Z generated it, because you generated it. Right? So that is the core trick. So basically, if you do this, then it allows you to minimize this KL divergence, because now you have an implicit way to sample from this true posterior distribution. But this comes with one major caveat, because like when you do it, like the data that you get, X actually comes from your model distribution. So this is my model generating data instead of nature giving me data, instead of this. So you are really not minimizing the same objective. So remember, when we use variational lower bound to maximize the likelihood of a model, we are maximizing variational lower bound with X drawn from nature as opposed to your model. And when we try to minimize the KL divergence from true posterior to approximate posterior with samples drawn from your model, then like it's not guaranteed that you make progress. So the most extreme case would be the support of your model distribution and the nature distribution is totally disjoint. So you would like your model would generate a bunch of samples, but like they would be things that do not occur in nature at all. Then essentially your model would get no training signal to converge to the true data distribution. So there are some flaws, but it's still usable as an algorithm. And the reason it's called wake slip is really it's broken down into two steps. There's a step called wake phase. In wake phase, you would sample data from nature, and then you would sample approximate posterior. You would sample Z from your approximate posterior. Like now with this X and Z, you can construct your variational lower bound. And then what you would do is you would maximize your variational lower bound with respect to theta, which describe the conditional model, and beta, which describe the prior distribution. So now you can do that because like these two terms are not defining the distribution. So you can just draw stochastic samples and then maximize them. Now you see that like in the wake phase, it actually does not train your approximate posterior at all. So if I keep running wake phase, what will happen? Right, so if you keep running the wake phase, your approximate posterior is just at initialization. So it could be really good, like it could be right exactly what you want, but it could be super crappy. And if it's super crappy, then you would not make much progress in your marginal because like you know that there's always a gap that is how good your approximate posterior is. So that's where the second phase comes in, like what's called a slip phase. So the slip phase, like all these interesting terminologies really come from like when like all these machine learning algorithms are heavily neuroscience inspired. So like you have this slip phase where the model is streaming. So basically you say in the wake phase, I observe the data and then I try to explain the data in the real world. And then in the slip phase, I would generate samples for my own beliefs. And then I would try to have my approximate posterior to match my own belief, basically. And then that's how you do it. And then in the slip phase, you basically do the usual maximum likelihood to train your approximate posterior. And then you can do that because you generate X yourself. Yes? Yeah, so the reverse KL is Z drawn from P of Z given X. Right, so if we draw from the prior, and then we draw X from P of X given Z. And then now, at this point, you can plug in this part of the KL divergence. So let's write it out. What does that mean? So that means log of P of Z given X minus log of QX Z. Right? So this part does not depend on Q. And then what my claim is that, Right, so this is my claim. you can do this. And then the effective z that you get from there would be as if it's from the true posterior. So this is not like, it's not totally intuitive-wise the case, but like it's a theorem called unconscious statistician, or something like that. It's basically, it basically just means like this is equivalent to z drawn from prior, and then x drawn from conditional, and then another z prime drawn from the true posterior. And then you evaluate the term under z prime. And these two things would be equivalent. And intuitively, I'm not going to go through the derivation here, but intuitively it makes sense, because what does the true posterior really mean is that for any given x, what would have been the z that generated it? And because now I have the actual generated path of z and an x, so the observation that you get would be as if you are sampling from the true posterior. Yeah. So for the function that's living inside, like these two expressions would be identical. So basically, you just draw z, and then you draw x, and then you try to fit your posterior model to whatever z that it was. So pretty simple algorithm. And that's how you do it. And let's see. So question so far? Yeah.
So in the split space, you first draw the z and x, right?
You first draw z, and then you draw x. That's the only sampling path that you have.
Then for the KL, you still need to draw z.
You don't. You just plug in the z. You plug in the first z that you have.
First z and
Yeah.
okay.
Yeah. Cool so far? So, up until now, what we have been saying is for each data point, it needs to have its own approximate posterior, because each data point's posterior is going to be different. But this is not quite scalable to large data sets. And like if your data set is streaming and all new data is always coming, then it quickly becomes fairly expensive to optimize. Why is that the case? Because like as your basically as your model changes, like always you need to optimize it from the initialization, unless you store an approximate posterior per data point, but that would not be tractable if you have large data sets. So it would be great if you have something that could sort of store the progress of this approximate posterior and then amortize it across different data points. So really, what's shown here is that instead of saying we have one queue per data point x, now I have a neural net that takes in data point x, and then it would output the sufficient statistics of the distribution that describe the queue. So now you have a distribution that is approximating, now you have a neural net that is approximating all of the queues together. And then what is usually called, this is called in the sort of autoencoder parlance, this is usually called an encoder, because this network essentially maps from observation space to noise space. And then the conditional model of x given z is usually called the decoder, which decodes some data point from a latent space. So let's see. So that's that. And basically, everything that we have built up so far, variational inference, variational lower bounds, plus wake-sleep algorithm, this is, we actually have been studying a paper that is 2-3 decades old, and it's by Diane and Hinton. It's one of the first latent variable model that people semi-make to work. And this is meant to say that, like, I mean, you have you have heard of like VAE, different kinds of latent variable models like a lot nowadays, but this is actually a pretty old idea, like pretty much everything in machine learning. And there are reasons that it was not popular back then. Like there are like problems that it could not solve. And what we're going to look at next are essentially how can we take some of these ingredients and then add in some quite modern tricks that make them a lot more scalable and then deployable to large data sets. Let's see, Alvin. So I will switch from here to Alvin. Basically what's going to come up next is we would look at ways to directly optimize the variational lower bound instead of trying to sidestep it through wake-sleep algorithm.
So far we've seen the wake-sleep, and Pieter pointed out how it's kind of inefficient, not very scalable. So the other way to optimize the variational lower bound that we've derived is what we're going to see now. So remember that our objective is this. We want to figure out parameters of the encoder and the decoder, theta and phi respectively. The decoder is theta, encoder is phi, such that we want to optimize this expectation of this three terms inside. So let's look at the optimization with respect to phi for now. The optimization with respect to phi is of the form where you have a distribution whose parameters are phi, and then you're trying to optimize some function of the samples that are acquired from the distribution. So this is of the form expectation over z, sample from q phi of some score f of z. So this particular form of this particular optimization problem is a pretty well studied problem in reinforcement learning, where there is no assumption made on the what you know about f, any analytic form of f, or anything like that. You just assume that you can evaluate f for any given z, but you don't really know what it is. So how do people do that? So obviously you want some gradients with respect to this quantity that you're trying to maximize. So you want a gradient with respect to phi of this expectation. And there's this really cute trick. I'm pretty sure like almost all of you might have seen this by now. So where you multiply and divide by the f of z inside. So first of all, gradient of the expectation is expectation of the gradient modulo all mathematical requirements. So then you multiply and divide by f, and you get the grad log probability of actually there's a typo here, so it should be grad log f of z. So we'll correct it. So once you do this, actually I can write it down on the board if that'd be better. So you want this particular thing. So let's just write this as P of Q phi of Z, assuming like discrete. You can replace with integral for continuous. So you want this. Then you just multiply and divide by Q phi. So this becomes and then we can replace it with the expectation inside. So the problem with this is that it has a very high variance gradients, which I'll show you why in the demo. But so you need a really good estimate to. You need several samples of Z to get this right. So another way to do this is to use this pathwise derivative estimator, where you reparameterize your z as a deterministic function of some noise variable epsilon and parameters phi. And epsilon could be sampled from a very fixed noise source, very simple noise source that you can fix to be like a standard normal Gaussian. So the expectation of z coming from Q of f of z can now be rewritten as expectation over epsilon of f of this deterministic function. So this is still, so the reason we do this is because when you can take the derivative of f, you can just get the exact derivative of f with respect to phi, but the expectation can be over the noise sample from very simple fixed noise source. Turns out that the variance of this gradient estimator is much lower. It's much more stable and more effective in practice. So let's just check out a demo where these two things are shown. So the problem, this is going to be a very simple problem. It's like too simple. You might think, why are we even solving this? Just to highlight the point mainly. So the problem here is to move the coordinate of this particular Gaussian to this target location. The target location is phi comma phi here, and the red points are just samples from this Gaussian, and this ellipse actually shows what the Gaussian is. And the important thing to note here is we are not worried about the variance here for now. So the parameter that we're trying to optimize is just the mean of this Gaussian distribution. So this black arrow denotes the direction we want to go towards as far as the mean is concerned. So here comes the pathwise derivative estimator. So let me just run you through the code. So you sample a bunch of standard normal Gaussians, and then you're reparameterizing the actual distribution by adding the mean here. The standard deviation is fixed to be 1, so there's no multiplication term. So the reward function that we are trying to optimize, that is the f inside, is just the distance between the target location and your current location. So the derivative of that with respect to the sample is just going to be the distance vector. So that is your gradient estimator, and you're averaging over the samples that you drew from the fixed noise source, and you're changing your mean to your parameter to in this particular direction. So, and here's how the score function estimator or the likelihood ratio estimator is implemented. Again, you start off with the same sampling mechanism. Your reward function is the same. Now the difference here is you're going to use this grad log with respect to mu, your parameter. And for a standard normal, for a Gaussian with variance 1, you can check that this is actually equal to the sample minus the parameter. So you can just, so because the log probability of Gaussian gets into x minus mu by sigma. So therefore you can have the gradient estimator to be equal to, so you just take the dot product of these two, the reward times this grad log prob, average it, and take a step in the direction. Note that we have a step size. It's like the learning rate in the any kind of optimization. So let's visualize what happens. So here's the score function estimator. I'll show you a case that actually works. Let's see if you can it does something meaningful when we have say when you draw 20 samples every time. So you start off with this at 0 and you want to get here. Note that it tries to get towards the green location, and as you keep increasing, as you do more iterations, it's going to get closer and closer. But note that I had a lot of samples each time. I sampled 20 noise sources every time. So let's see what happens if you change this to say 2 samples. And I want to show you that variance problems precisely here. So the variance actually matters when the number of samples is very small, because the variance depends on the sample size, 1 over n. So you can see how the updates are pretty unstable. For instance, here the mean is being pushed really far away. So you can see how unreliable the gradient estimates are. So that's the issue with, it does get to the target location at some point, but it's pretty unstable. So what happens if you just use, for instance, one sample? So you can see like how, let's wait for it. Yeah, so it does sometimes work, then it gets away. So it's pretty unreliable. All right, so let's see what it is for the pathwise derivative. And let's directly start away with one sample. You can see that even with just one single noise sample, the pathwise derivative is pretty stable and keeps getting closer to the target location. So this is why, mathematically you can probably prove that you can write down the variance and see for yourself for specific cases. But in practice, this made a big deal because, actually one of the main things about the VAE paper is this reparameterization trick, because when you want to implement it with SGD, with deep neural nets, you can just have a single noise epsilon in that expectation, and just run SGD on the encoder and decoder, and everything would work. So we'll see how the algorithm actually is implemented. All right. So, like we saw, there's a caveat for the pathwise derivative. So note that you do need the latent variable to be continuous. Only then you could have written it as a deterministic function of another fixed noise source. So we're dealing with Gaussian latent variables here. So you could have actually seen it in the implementation of the code, where if I wanted to sample a bunch of Gaussians from a mean and a standard deviation, I would have just added the mean and then to a bunch of samples from a standard normal Gaussian. This is like you guys are probably doing it for all along. Whenever you sample any Gaussians in NumPy, this is literally the reparameterization trick, where you just do mu plus sigma times epsilon, and that becomes a normal Gaussian with parameters mu and sigma. So this is written in math, where if you have the covariance matrix notation, you need to write it as sigma per half, because it gets scaled to square. And so note that the variational lower bound, earlier it was written as an expectation of over z coming from q phi of z given x. Now it's been converted to expectation over epsilon coming from a standard normal, where the z is actually written as a deterministic function of epsilon. And you average this over data points from your data distribution with just a single noise vector sample every time. And you run SGD and optimize theta and phi. This algorithm is called variational autoencoder. Note that this particular the posterior with the approximate posterior with the prior, you can write it down analytically if you specify q phi of z given x as a Gaussian distribution, and also have the prior as a Gaussian distribution. So the KL between two Gaussians can be analytically written down in terms of the parameters of the two distributions, and so they just become a function of the mu and sigma of your posteriors. So why do we even call this an autoencoder? Like it's variational, we know that. The reason is you can look at the two terms in your variational lower bound, So the first term is log p3 of x given z, expectation over the posterior samples. So that's like a reconstruction objective. You're trying to reconstruct your data point x from your noise source z that you sample from the posterior. So you call this as the decoder, as Pieter pointed out. So in an autoencoder as well, you have the decoder. And the second term is like some kind of a regularization objective that prevents your posterior from fitting one z to every single x separately and happily optimizing the log likelihood objective. So it has to make sure this particular term makes sure that you cannot just you have to be regular in terms of what distribution you're optimizing for p. So you can think about this as the regular autoencoder objective, and then this term as trying to make sure that the latent space is some kind of a standard normal Gaussian. All right. So one obvious decoder that we can think of is just to have a Gaussian for every value. Let's say a diagonal covariance Gaussian, even for the decoder. So let's say you're outputting pixels and you want to output Gaussians for every pixel condition on the latent code. So you could do that. So that's the decoder here. The theta are the parameters of the decoder. And the encoder is also another Gaussian where you just output mu and sigma with respect to phi. This was how the original VAE was implemented. For MNIS, it was implemented as so this distribution was not Gaussian. It was a Bernoulli distribution. So based on that, your log likelihood objective becomes a sigma cross entropy loss, or it could become the standard likelihood objective for a Gaussian. So depending on what decoder distribution you pick, the way you implement it changes. So here's like the results from the original VAE paper. So AEVB is autoencoding variational bias. That was the title of the paper. Wake sleep is the algorithm that Pieter described. So it's evaluated on two different data sets, MNIST and Frey phase. Frey phase is just a bunch of, I think 2,000 phases of this researcher named Brendan Frey. So let's see. So NZ is actually the dimensionality of the latent space, the number of latent variables. So you can see that the negative log likelihood of the variational autoencoder is better than the negative log likelihood of wake sleep. And also, you can see that this is not specific to just VAE. Even wake sleep works as you keep increasing the dimensionality of the latent space. So this shows that doesn't overfit as you increase the capacity of your encoder. But you can see that on the Frey phase data set, it's much better than the wake sleep. So I think it was pretty important at the time. These are some visualizations of the generated samples from VAE. On the left, you pick a 10-dimensional latent space and train a VAE, and these are the generated digits. On the right, this is some kind of a clever visualization where they pick a 2D latent space, 2D Gaussian, but to get the vectors for this visualization, they sample uniformly spaced, linearly uniformly spaced points in a 2D rectangle, uniform rectangle, 0 to 1, and use the inverse CDF of the Gaussian and get the points in the 2D Gaussian and pass it through the decoder. So you can see how like the stroke interpolations are very nicely smooth over here between 6 and 0, 7s and 1s over here. Also, you can see how the slope of the strokes are the same for all the columns. So it is learning the right kind of disentangled latent variables. And in terms of log likelihood performance, we've already seen autoregressive models. So the log likelihood of this model this model is pretty old, like it's kind of 5 years old by now. So it's pretty far away from the negative log likelihood of, say, the model that you guys implemented, Pixel CNN. So obviously the performance is lacking compared to powerful expressive autoregressive models. So that means we need to bridge this gap between